Welcome to the statistics learning session today. In this presentation, we'll explore process of finding the maximum discrepancy between empirical distribution function Fn and cumulative distribution function F0. This computation is essential in statistical hypothesis testing and will focus on practical methods of calculating a guess, statistics Tn, and its relationship to the supremum of a Brownian bridge. Now let's dive into it. In last session, we showed that there are 4 points and each point increases by one half of 4 and two half of 4, 3 half 4, 4 half 4. And that's how it went on from this to here. Now, we're going to find the maximum discrepancy. The greatest discrepancy between Fn, empirical distribution function, and F0, cumulative distribution function, is achieved at jump points of Fn. This is jump points of Fn. This is because F0 is increasing as CG must be, while Fn is piecewise constant. This is piecewise constant. This is constant. This is constant. Piecewise constant. Now, we have defined Tn, which is a supremum of Fnt and F0. Do you know how to write that? We discussed about in last session. Think about how to write the Tn. The Tn should be written as Tn equal to sup of T F not T F not T. So this is a supremum of T, and the jump points, this can be expressed as Tn. At jump points, this is general definition. At jump points, this can be expressed as max. At jump point, this can be expressed as like this, where this can be said as a Fn xi, and it can be said as Fn xt minus 1. Now, so we have to compute the how we have to find out why Fn xi is equal to 1. Why Fn ix is equal to, actually this should be belong to this and this belongs to this. Why Fn ix is equal to 1 by n? It is because at each point it jumps by 1 over n. That's why it's 1 by I by n. And how about Fn xi minus? It is a 1 point behind. We are talking not about this point, it is, but we are talking about 1 point behind. That's why it's I minus 1 divided by n. That's why it's like this. Now if we have to evaluate discrepancies at each point, we will compute the two discrepancies. Do you know what are those discrepancies? Think about it. The first discrepancy is this: I minus 1 divided by n minus f naught I xi, and I by n minus f naught xi. These are two discrepancies we have to compute at each point, and we will take the maximum of those. Now, once we do that, finally what we do is we have to take a maximum of all maximums. So at each point we take a maximum of this and then we also compute the maximum, all those maximums. So it's going to double maximum. Now let's simplify the calculation here. We are simplifying calculation by substituting. Initially, it should be like this, but we are substituting it by I by n because it's easier for calculation. So what's the practical implementation of this? Think about it. In practice, this reduces computation of Tn to evaluating maximum over 2n values. So Tn is going to be I through n. So we are not doing for all the values, but only 2n values. And it reduces the computational efficiency. It improves the computation efficiency. And how it is related to Brownian bridge? Tn corresponds to supremum of Brownian bridge, which has known probability density function. Pre-compute critical values of the supremum can be used in hypothesis testing. So let's summarize what we learned today. The computation of Tn simplifies the process of comparing empirical distribution function Fn to a theoretical cumulative distribution function F0 by focusing on discrepancies at specific jump points. This efficient approach reduces computational complexity and connects to established statistical properties, such as supremum of absolute value of Brown bridge. With precomputed critical values, these test statistics can effectively utilize in repeated hypothesis testing scenarios. That's all for today. I'll see you next learning session. Thank you so much. Have a nice day.